magnetic I/O type. So say RIO for restricted I/O, and then we can sort of bring in whatever side effectful operations we want and guard them appropriately. Now, this is obviously a very trivial attack for anyone who's familiar, so basically anyone in this room in Haskell. So we'll just look at a few of them very quickly. Obviously there's unsafe functions, like I could use unsafe perform IO and pretend something that is an IO action is actually a pure function. I can use the unsafe primitives that actually are used to implement unsafe IO. I can use the foreign function interface to access a C function and pretend it's pure as well. And so the question is, how do we prevent these kind of attacks? So that's what Safe Haskell is about. We want to be able to essentially trust the types to some sort of definition of what trust is, so that we can bring in code and then we can just use the type system to reason more explicitly about it, particularly in a context where security is paramount. So the first thing we're going to do is we're going to define a restricted subset of Haskell where we have enough guarantees to sort of reason about what the types mean and what is expressible in this language. And so we're going to compile any code that we want sort of high-level guarantees about in this restricted subset. So with a language pragma -x safe. And the intuition here that we're trying to get is that types don't lie. And so obviously if it's a pure function, it should be a pure function. If it's an IO operation, it should be an IO operation. So for example, let's say we try to compile this previous example where we're doing a foreign function import with the safe subset, then we're going to get a compiler warning saying that anything that is in the safe subset of the language and uses the FFI has to be importing that external symbol in the IO monad. Since this is a sort of a symbol that the compiler can't reason or check about, so we have to take the most conservative approach and put it into the IO. So you can still do foreign function imports, it just has to be within the IO monad. And so the restrictions that we get in the safe language sort of fall along three categories. The first is type safety. So obviously you have the big obvious ones like unsafe perform IO and unsafe coerce. The foreign function interface can only import things into the IO monad. Previously, when this work was initially done, generalized new type deriving also had some sort of essentially bugs in it that allowed you to do unsafe coercions through generalized new type deriving. This has been fixed in I think 7.10 or 7.8 with the role mechanism that GC now has. And also previously you could define your own instances of typable, and so through that do any arbitrary coercions that you wanted to. But since we added support for polymorphic kinds, you no longer can do your own typable instances. So these two ones have been fixed. Module boundaries essentially is, if I have a module A and I only export 3 symbols, maybe I only don't export any of the constructors of a data type, then you shouldn't be able to access any of the symbols that aren't exported. So template Haskell, for example, allows you to violate this. Generalized new type deriving does, although it's a little bit subtle. So historically, generalized new type deriving allowed you to violate this sort of arbitrarily, but as I said, it's been improved, sort of somewhat fixed with the new role mechanism that generalized new type deriving relies upon. The problem that we still have with it is that it's fairly subtle. So the default with where generalized new type deriving, depending on how it's used, is that what is it? It's a representational types, I believe. Essentially, basically, if you don't add a certain annotation to some of your types in the way that generalized new type deriving works, it allows you to see through sort of the module boundary list and still access a constructor that was hidden. Semantic consistency is basically what we want to have a guarantee is we want to have a guarantee that, let's say I have a module A and it compiles. I'm now going to import a new module in that code. So in module A, I'm going to add a new import. We want to guarantee that by adding a new import to a piece of code that already compiles, you don't change the meaning of that code. So for example, obviously rules can defy this, and overlapping instances can defy this because the new import may define a more specific instance. We want to sort of have the guarantee so that if you have some trusted code base and you're going to import unsafe code into that TCB, that you're sort of have a guarantee that the unsafe code can't alter the meaning of your existing code base. So one nice thing about this safe subset is it's really just like a checklist, so we can infer the safety property of an existing module. It's like a very easy inference. It's just sort of checking it abides by these rules. And so the second step here is we need to sort of ensure transitively that the imports that a safe module makes are also safe. So for example, if we have this piece of code here, module unknown, and it's importing module A's and module B's, then we need to have some sort of guarantee here that A and B also abide by this restricted subset. And one choice we could make here is we could just enforce that everything transitively has to be within the restricted subset. So in the previous example, both A and B would have to be in the safe subset of the language. Now this is overly restrictive though, because these unsafe features exist for a reason, otherwise we would have got rid of them years ago. And so for example, the sort of very widely based data byte string, as a lot of you know, is built on top of unsafe primitives, but presents to the user an interface that doesn't allow you to violate the sort of safety status of the language. So even though internally when you do like a cons, it's using sort of pointer arithmetic and doing like a memcopy, you aren't exposed to that as a user. You get an interface that only exposes what appears to be a pure sort of safe list-like representation of byte strings. And so we'd like to obviously be able to support code like data.byte string and allow its use in safe restricted code. And so what we're going to do is we're going to extend the number of modules you consider. So we have X safe modules, and now we're going to add a second type of module, X trustworthy modules. And so the point of X trustworthy modules is they shouldn't allow the violation of the three properties that we defined earlier, trusted types, module boundaries, and semantic consistency. But the guarantee that they don't allow a violation of those three things is only provided by the author of the module. So the compiler doesn't do any checking of this, it can't do any checking of this, and it's up to the module author to sort of, just provide that guarantee sort of as a human contract. And so one thing that's sort of interesting about trustworthy modules is safety is a little bit actually more than trusting the types. So for example, maybe we define a vector type that's going to have a pointer to some contiguous piece of memory allocated on the heap. It's going to have a length for the number of elements currently stored in the vector, and it's going to have a capacity for how long the actual buffer is that is pointed to by the pointer. And so this is this is a safe function that is using unsafe features of the language for doing indexing. And so, we are violating the type system here, but in a sort of safe manner. But at the same time, this is a sort of unsafe function, but the one that doesn't actually violate the type system, right? Like, so in here, we're going to grow the vector, but we're going to do so without any sort of bounds checking. We're just going to, say that like the vector now contains n more elements. And if we decide to add like a, infinity to this, whatever, like a million to this, and it was, now the length of the vector may be greater than its actual capacity. And so the previous function that violated type safety, but should hopefully only do so in a way that exposes safe interface, can now basically violate some of the invariants that vectors try to provide. And so even though this function is completely type safe, I would argue it's an unsafe function due to the sort of invariants that vector is trying to impose. Right, and so these sort of invariants which the sort of programmer can reason and know about, but aren't necessarily enforceable or require a lot of complexity to enforce in the type system, would be that pointer actually points to an array, and that the array is of size capacity. The first len elements of the array have been initialized, and the length is less than the capacity. And one thing that's sort of interesting about this is when these fields are private that sort of allow you to sort of enforce these extra invariants or like alter these invariants, then the scope of the sort of unsafety of these functions ends at the module boundary, right? So like the way you implement these sort of unsafe features is you have a module boundary where any of these invariants are enforced internally and you're aware of them, and then externally what you expose doesn't allow these invariants to be violated. So you could ask, like, okay, well, could we remove trustworthy? And if you want to, I think there'd be basically two approaches. One would be a more powerful type system, and that's obviously like a sort of ongoing active area of research in the PL community. It's open question whether the complexity would be too great for a lot of use cases. And the second might be using some form of dynamic checks and just throwing exceptions for violations. But obviously these unsafe features sort of exist for a reason, and one of the large use cases of them is for performance. And so adding in bounds checking, for example, for a lot of these use cases would be too prohibitive. Yeah, and so I guess I just wanted to sort of sum up where the purpose of a type system kind of goes beyond type safety. It's also obviously for establishing safe abstractions. And so safe modules, right? They have a restricted language, and and safety sort of is enforced by the compiler. And with trustworthy modules, the author is trusted to bound the unsafe functions to the module boundary. And so at this point, so what's missing, right? We've got X safe modules and we've got X trustworthy modules. And it's obviously sort of the final one is, the unsafe modules. And so you can explicitly type something as being unsafe, although if you're using any of the features that are out of bounds from the restricted language, it will be inferred. But you still may want to type something as unsafe because of what we talked about earlier, where you may have code that is perfectly type safe, but allows the invariants that your trustworthy modules sort of need to guarantee to be violated. So for example, like a lot of packages will expose a .internal module, and sometimes those internal modules will violate type safety, but sometimes they won't. But they do allow the invariants to be violated, and they need to be used with care. And so you would want to explicitly mark a module like that as being unsafe. And so I want to sort of like now walk through how this all fits together. And so when I ask the question is, let's say I have some client code, and it's got to import a module M. And the question is like, does this compilation succeed? Like, so can this client code import M? And this is under the scenario where all of M's imports are trustworthy. Right? So you've got some client code importing M. Everything import is trusted. And I'll get into later what trusted means, but just take that as like a given for now. So let's say the module M being imported by the client is written in the restricted subset, and so it's compiled with Xsafe. Then the import of M will be allowed. If the M is compiled with Xsafe and not actually in the restricted subset, then compilation wouldn't have succeeded over M to begin with. If M is marked trustworthy, then regardless of whether it's using the restricted language or the full language, it will be allowed to be imported. And if M is marked unsafe, then it won't be, the importation into the client code won't succeed. And so obviously there's a very large flaw here in that I can just mark any of my modules trustworthy and compilation will succeed regardless. And so we need some ability to sort of control that. And that's just it. So like I said, when I mark my modules being trustworthy, that is the module author sort of offering a human guarantee that doesn't violate any of the three properties we talked about of type safety, semantic consistency, and module boundaries. But you then, as sort of system administrator, someone compiling code, want some ability to sort of control that and reason about that further. And so, once again, so we have a module M, and it's in a package tree, package P, and we're going to say that like the module M is trusted if either of these two things succeed. Either the module M is actually is marked safe and all of its imports are trusted, or the module M is marked trustworthy, all of its safe imports are trusted, and the package that it resides in is trusted by the system administrator, so basically by the person doing the compilation. So with your package database, you can mark packages as being trusted or untrusted, to basically control whether or not the importation of trustworthy modules is allowed. So, for example, like in GHCI, I can just do set dash trust byte string, and now like any of the trustworthy modules in the byte string package will be allowed to be imported by code using the safe subset. And so one question we get is, what do we do then when we're inferring safety, right? Because the sort of safety status depends now on the configuration of the machine doing the compilation. And so what we do is we just assume that all packets are trusted at compile time, and then at link time we basically recheck that and potentially fail then if a trustworthy package, the trustworthy module is no longer in a package that's trusted. And we have one sort of small extension to the language where we allow imports now to be done with a safe keyword. And this is only really useful in the trustworthy mode of operation. And the point is just to sort of give you a little bit of flexibility as a module author to limit what you're claiming, right? Like, so I might be writing a module M, and I only want to sort of make the claim as an author that my module is trustworthy if like I can also sort of rely upon the fact that the data.bytestring package is also trusted. So just like, so it gives you some scope control over your claim.
Can I ask a question there?
Yeah.
So if the author does that, are they basically saying, I only claim that the code that I create is trustworthy given that you trust this? It's like, if you should only trust my code if you also trust this code that I've marked safe.
Yes. Yeah. Exactly.
If someone's trying to create a set of packages that allow them to run unsafe code in some context, can't they just create a package that they mark safe that uses a package that they created also that they mark trustworthy, but that's actually not trustworthy, and then everything will trust their safe package?
So they're getting a package marked safe. They rely on a package that's has some trustworthy modules that violates things. Okay, but now they have to convince me to trust that package, right?
So so if you mark something safe, so it is possible to mark something safe that is using a trustworthy module, right?
Yes. Yes.
I thought your declaration before said that anything that's marked safe is just going to be trusted automatically, or does it also always look at all its dependent modules?
It looks at all of its dependent modules. So like it's safe, but then all of its imports have to be trusted.
Okay, so basically the entire tree of things that are marked trustworthy have to be in your whitelist.
Yeah.
Got it.
Yeah. Right, so essentially we just divide this X-trusted world in half, where it succeeds if the package is trusted and it doesn't succeed if it's untrusted. This is just like the sort of silly example where M has untrusted imports. So sort of a little bit on your question, right? Like if N has any untrusted imports or sort of transitively so, then it'll all fail. So you can kind of see this by, if you're in GCI, you can type trusted some module name and get the sort of the status of everything. So it's saying here data.text is a trustworthy module. The package it resides in right now is not trusted. And for this module to be considered trusted, you need to trust the following package dependencies. So you need to trust text, byte string, and base. And at the moment, 2 of them are trusted and 1 of them isn't trusted. So one quick question here is like, so what doesn't save Haskell handle? And so for example, like, should this compile, right? Like, we're going to generate a random offset. We're going to, poke an element at a random offset from the pointer. Very, very likely this will segfold. And the answer that we've said is like, this is completely fine. And the reason for that is essentially that securing all of I/O sort of intuition is basically like a lost cause. That you're gonna have to sort of secure sort of things like this, add bounce checking to various things. You're also gonna have to potentially bring in guarantees about like, okay, can they do like a ptrace call? How do we stop them basically manipulating any avenues where they can manipulate memory arbitrarily? And so the approach that we kind of took based on intuition was like that I/O is just too large of an attack surface for us to reason well about and to secure. And so this is perfectly fine, but if you're running something security critical, then you shouldn't be doing sandboxing, right, where you're relying on some kind of thought of properties of I/O, and you should be using your either pure functions or doing what we saw earlier, defining your own I/O type that has restrictions placed upon it and sort of just whitelists what you want to bring to scope. Yep. Alright, so like I said, Safe Haskell got first released in 7.4, there was very beta in that point, sort of the first real good release was more at 7.6. It's been like small refinements since then. It's used by, right now in terms of what I know of, like widely, one is LIO, which is a library that we developed in our lab for doing information flow control at the language level in Haskell. We then went on to use that for building a secure web framework called Hails, which is sort of all around doing, imagine like you want to write a website like Facebook and you want to have third-party authors write plugins that operate over private user data, and you want to offer strong guarantees about whether or not their privacy policy can be violated. And so Hails is a web framework that facilitates building a website of that nature. Jitsi.io, which is a sort of very simple online interpreter that I wrote to play around with Safe Haskell. And you may or may not have noticed, but it's actually always visible to you because in the top right corner you'll see the safety status of all modules when you go to Hackage. And then in terms of how safe Haskell is, so these are numbers I ran maybe 6 months ago, and this is basically just trying to compile all of Hackage and infer what infer modules are safe or unsafe. Right now it's about a little bit over a third safe and 2/3 unsafe. A lot of that is just sort of due to transitive issues, and so I think if I sit down and sort of like go through the list and there's a few sort of key modules, then we can like push it up a lot. And one way to sort of maybe look at it a little bit is like, okay, well, let's do the compilation again, but this time we're gonna just assume when we compile a module that all its imports are trusted. So we're going to sort of ignore whether or not the actual imports are trusted. We're just going to try compiling that module in the safe subset of the language. And if you do that, you find that actually about 85% of Haskell modules are buildable in the safe subset of the language. And so that sort of seems to indicate that despite the fact that like only a third of them right now are safe, actually 85% of them work within the restricted subset of the language. And so most of the sort of failures are coming from modules that they depend upon, which hopefully can be fixed over time. So we want to use Safe Haskell today. Like I said, there's 3 pragmas: safe, trustworthy, and unsafe. And then also you can put on 3 different warning flags. Warn if my module is inferred unsafe. Warn if my module is marked trustworthy, but it actually could be marked safe. So I could like sort of upgrade essentially my trust. And if you really want to, you can do f-warn if my module is safe. So that's all I have to say. So the sort of design doc, if you want to dive in, is on the Haskell Wiki. There's a page here for Stanford with like the paper on it. You can play around with the REPL. So any questions or anything?
So you said as one of the premises of Safe Haskell is types don't lie.
Yeah.
But one sort of contrarian position here is, sure they do, we have exceptions working everywhere. We have error call. We have a whole bunch of things, we have a whole bunch of bottoms everywhere that aren't being ruled out by Safe Haskell. Can you talk about why you made that design decision?
Um, I mean, we want safe Haskell to be pretty minimal. I think that's like largely what it comes down to, because ideally, like, you know, if you could imagine if you were starting this from day one, you might do things very differently. But we're trying to retrofit this on the existing language, and we want to get as broad adoption as possible. And so I never really thought about how I would go about sort of trying to like limit exceptions further and limit bottom further. But to me, that's my intuition is that that would be fairly invasive compared to what we can do right now. And like the amount of code that might now become sort of unsafe is far greater.
So like things like partial case matches and things like error calls would, any module that uses that at all would be unsafe.
Yeah. And also like you can imagine offering strong guarantees, and that brings some benefits with the trade-off that adoption might become more difficult, and so the amount of useful code you can sort of bring in becomes less. And at least with okay, we might it might throw exceptions, but at least we have ways to like deal with that. Right, like if my code safe faults, I don't really have a sort of a way with the language to deal with that. If my code does a partial application and throws an exception, like I have some way of handling that. Like I can at least capture that at some point and take some kind of action around it. Any other questions?
If no one else has
Yeah.
any. You decided to have safe be a module level thing.
Yeah.
Why not a function level thing?
That's a good question. You could do either. Our intuition basically was that the existing conventions in the community were at the module level, right? You look at before, today and before Safe Haskell existed, you looked at modules and they would have like a .internal module, a .unsafe module. And so we sort of went along with that as like, okay, let's like follow these conventions, it'll be easier to adapt to it. At least, and also I guess the other intuition is, like I said, with trustworthy modules, you can kind of look at them really as needing to operate more at the module level because of, you need information hiding to sort of hide some fields to like give those extra variants. One thing you could imagine doing, because I think at times doing the sort of safety at the module level has problems. Like one of the packages that this doesn't work well with actually is the vector package, because the vector package has a lot of variants of functions that are unsafe in different ways. And so at one point I worked with Roman to split that all up and had like a few versions of vector that used safe Haskell. He ended up reverting that basically because he just found that like because of the number of modules he needed to create with module level annotation, it was like too much of a burden for him. So I think what might be a nice thing to do is keep sort of like a module level guarantee where you're like, okay, I say this is safe or trustworthy, but then like allow selective downgrading of symbols. And so you'd have like, okay, like I said, like, okay, my module's trustworthy, but now I'm going to annotate individual functions as being like something lower than that, so unsafe. I could see that being, maybe a nicer design point that's worth exploring. Anyone else? Yeah.
So you mentioned it would be really hard to control I/O. It seems to me that that's kind of, there are a lot of sandboxing technologies that kind of do it at that level. The JVM or native client or the web sandbox, etc. So what are the advantages of this kind of higher level safety versus the existing low level sandboxing?
I think one aspect is it's much more. It's like more. I would argue it's more controllable in the sense that something like native client, right? Like if I want to impose like extra guarantees, like it's not clear to me like how I like necessarily do that. Like I can take their technique and sort of extend that. But like with this, right, like I just like write a library, and so sort of the deployability of this, and where it's just like a language level feature, is like much higher, I would argue, and like sort of my control and expressivity, I would argue, is higher than what I get with something like more like an OS level sandbox. Like I said, one of the motivations was doing information flow control, and it's for what we want to do, we want to be able to do like label individual values in the language as having like a certain security policy. It's how you retrofit something like an OS level sandbox to achieve that is not sort of straightforward.
I think there's some applications I can think of in like the Hail web framework, for example, describes problems like being able to allow third-party developers to write plugins to something like Facebook that could, securely use and like process third-party data.
Yeah.
You could do that with a powerful type system that you can trust by imposing some kind of interface that allows, a function that transforms data but doesn't allow it to be sort of escape that box.
Yeah.
Because
exactly.
they can't do any I/O to like send it to themselves.
Yeah.
Then that could be powerful.
Yeah.
But I mean, you could do that with
that's
low-level
exactly
techniques.
what we did, right? Yeah.
Right.
Yeah. It works really well.
Cool.
Anything else? Awesome. All right. Thanks, guys.